What does the future of ground combat look like when artificial intelligence, autonomous systems, and network-centric warfare converge on a single armored platform? Picture an infantry fighting vehicle that doesn't just transport soldiers to the battlefield. It thinks, adapts, and fights alongside them. Imagine a machine that can identify threats faster than any human crew, coordinate with drones and robots operating miles away, and survive weapons that would have destroyed any previous generation of armored vehicle. This isn't science fiction. This is the US Army's optionally manned fighting vehicle program, the ambitious effort to replace the M2 Bradley infantry fighting vehicle that has served since the 1980s, with a platform designed for warfare that doesn't yet fully exist. The Bradley replacement represents far more than just a new armored vehicle. It symbolizes a fundamental transformation in how armies conceive of ground combat in an era where the battlefield is increasingly transparent, where every vehicle can potentially be detected and targeted from multiple domains simultaneously, and where the advantage goes not to whoever has the thickest armor, but to whoever can process information fastest and act decisively on that information. The new vehicle, currently designated the XM30 in its development phase, must balance seemingly contradictory requirements, be light enough to deploy rapidly anywhere in the world yet survivable against the most advanced threats, carry infantry squads into combat while providing fire support that matches or exceeds dedicated gun systems, operate with full crews or autonomously depending on mission requirements, and integrate seamlessly into a networked force where information flows continuously between platforms, sensors, and commanders. The challenges involved in creating such a vehicle are immense. Technologically, the program must mature and integrate systems that are themselves still evolving. Artificial intelligence for autonomous operations, active protection systems to defeat incoming projectiles, advanced networking capabilities that function even under enemy electronic attack, and weapons that can engage threats across a spectrum from individual soldiers to heavily armored vehicles. Financially, the program must deliver capabilities that justify costs in an era of constrained defense budgets and competing priorities. Operationally, the vehicle must be reliable enough for sustained combat operations, yet incorporate technologies so advanced that they push the boundaries of what's currently possible. Doctrinally, the Army must develop new concepts for how this vehicle will be employed, new organizational structures to support it, and new training methods to ensure crews can exploit its capabilities. This is the story of how the Army's next-generation Bradley replacement is taking shape, the technological innovations driving its development, the doctrinal transformations it represents, and the challenges that must be overcome before it revolutionizes armored warfare. It is a story still unfolding, with outcomes uncertain and timelines subject to change, but it is also a window into how modern militaries plan for future conflicts, how they balance innovation against practicality, and how technological change transforms the fundamental character of warfare. The M2 Bradley infantry fighting vehicle has served the US Army since 1981, participating in every major American ground operation from the invasion of Grenada through the wars in Iraq and Afghanistan. Over 4 decades of service, the Bradley has proven itself a capable platform, combining the ability to transport infantry squads with substantial firepower from its 25mm chain gun and TOW anti-tank missiles. The vehicle's survivability has been enhanced through multiple upgrade programs that added armor, improved crew protection, and integrated new technologies. Yet by the 2010s, it became clear that incremental improvements could not address fundamental limitations imposed by a 1970s-era design competing against 21st century threats. The decision to replace rather than further upgrade the Bradley emerged from several converging factors. First, the basic chassis and internal architecture constrained what could be added or improved, like renovating an old house. There came a point where the foundations and structure simply couldn't support additional modifications without rebuilding from scratch. Second, potential adversaries developed capabilities specifically designed to defeat vehicles like the Bradley, including advanced anti-tank guided missiles, long-range precision fires, and sophisticated sensors that made the battlefield increasingly transparent. Third, the character of warfare itself was changing in ways that demanded capabilities the Bradley could never possess, regardless of how much it was upgraded. The transformation of ground warfare in the 21st century can be understood through several key trends. First is the increasing lethality and range of anti-armor weapons. Modern anti-tank guided missiles can engage armored vehicles at ranges exceeding 4,000 meters, fired from platforms ranging from individual soldiers to helicopters to unmanned aerial vehicles. These weapons employ sophisticated guidance systems, including fire-and-forget technology, top attack profiles that strike vehicles' weakest armor, and tandem warheads designed to defeat reactive armor. The proliferation of these capabilities means that armored vehicles face threats from more directions at greater ranges and with higher probability of kill than ever before. Second is the transparency of the modern battlefield created by ubiquitous sensors. Satellites, reconnaissance aircraft, tactical drones, ground-based radar systems, and even individual soldiers' equipment can detect and track armored vehicles. This transparency means that traditional approaches to survivability, concealment, and cover are increasingly difficult. If every vehicle can be detected, survivability must come from mobility to avoid being targeted, active protection to defeat incoming weapons, or sheer toughness to survive hits. The Bradley replacement must address this reality through combinations of all three approaches that previous generations of vehicles didn't require. Third is the networking of military forces into interconnected systems where information flows continuously between platforms, sensors, and decision makers. Modern combat is less about individual platforms fighting isolated engagements and more about systems of systems where multiple capabilities combine to create effects greater than the sum of individual parts. An infantry fighting vehicle in this environment isn't just transport and fire support for one infantry squad. It's a node in a network that includes other ground vehicles, aircraft, drones, artillery systems, and command posts, all sharing real-time information and coordinating actions. The Bradley replacement must be designed from inception as a networked platform, rather than having networking capabilities added as an afterthought. Fourth is the emergence of autonomous systems and artificial intelligence as military capabilities. Drones that can operate with minimal human control, robotic ground vehicles that can perform reconnaissance or logistics tasks, and AI systems that can process sensor data faster than humans and recommend courses of action are all transitioning from experimental technologies to operational capabilities. The Bradley replacement must not only incorporate these technologies itself, but also work alongside autonomous systems that will be increasingly common on future battlefields. This means the vehicle needs the computing power, communication bandwidth, and software architecture to function as part of human-machine teams rather than purely human-operated systems. Fifth is the changing character of great power competition and the kinds of conflicts the US military expects to fight. The counterinsurgency operations that dominated the 2000s and 2010s emphasized survivability against improvised explosive devices, rocket-propelled grenades, and small arms fire. Future conflicts against peer adversaries like China or Russia would involve high-intensity combined arms warfare with sophisticated enemy capabilities across all domains. The vehicle that could dominate insurgents in Iraq might be inadequate against Russian T-14 Armata tanks, supported by integrated air defenses, long-range precision fires, and electronic warfare systems designed to disrupt American military networks. These contextual factors drove the Army to launch the Optionally Manned Fighting Vehicle program as part of the broader Next Generation Combat Vehicle initiative. The program's name itself signals important priorities. Optionally manned indicates the vehicle must be capable of operating with full crews, reduced crews, or even autonomously depending on mission and circumstances. Fighting vehicle emphasizes that this isn't just protected transport, but a combat system capable of engaging and defeating enemy forces. The program's objectives go beyond simply replacing Bradley on a one-for-one basis. They aim to create a vehicle that fundamentally transforms how mechanized infantry operates. The program timeline has been ambitious, perhaps overly so, given the technologies involved. Initial requirements definition occurred in the late 2010s, with the Army releasing requests for proposals to defense contractors in 2019. Multiple companies submitted designs, and in 2022, the Army awarded contracts to 2 teams for the competitive demonstration and risk reduction phase, a process where competing prototypes would be built and tested before a final selection. Point Blank Enterprises and American Rheinmetall Vehicles teamed together as one competitor, while General Dynamics Land Systems and BAE Systems formed the other competing team. Both teams received contracts to develop prototypes that would demonstrate their approaches to meeting the Army's requirements. The requirements themselves are demanding and in some areas contradictory. The vehicle must provide protection against current and emerging threats while remaining deployable by C-17 cargo aircraft, the standard for strategic mobility. This creates tension because armor protection adds weight, and more weight makes air transport difficult or impossible. The vehicle must carry a full infantry squad of 9 soldiers, plus crew, while providing firepower equivalent to or exceeding the Bradley's 25mm gun and anti-tank missiles. It must have the speed and range to operate across extended battlefields while maintaining reliability that allows sustained operations without excessive maintenance. And it must incorporate advanced technologies for networking, active protection, and potentially autonomous operation, while remaining affordable enough to procure in meaningful numbers. The technical approach to meeting these requirements involves several key innovations. First, the vehicle is being designed with modular armor that can be configured differently, depending on threat environment and deployment method. In permissive environments, or when deploying by air, the vehicle might operate with minimal armor to reduce weight. When facing high-threat environments with time for preparation, additional armor modules can be added. This modularity extends to other systems as well. Weapons, sensors, and even internal configurations might be changed based on mission requirements rather than being permanently fixed as in previous vehicle designs. Second, the vehicle incorporates active protection systems as primary defense against anti-tank weapons rather than relying solely on passive armor. These systems use sensors to detect incoming threats and then either jam their guidance systems or physically intercept them with countermeasures before they reach the vehicle. Active protection has been employed on Israeli armored vehicles for years and proven effective in combat, but American adoption has been slower. The Bradley replacement assumes active protection as fundamental rather than optional, building the vehicle's architecture around the assumption that many threats will be defeated before impact rather than absorbed by armor. Third, the vehicle's design emphasizes computing power and networking bandwidth as combat multipliers. The onboard computer systems must process sensor data from the vehicle's own sensors, plus information received from other platforms across the network, fuse this data into coherent situational awareness, present it to crews in useful formats, and enable rapid decision-making. The vehicle must also be capable of controlling or coordinating with unmanned systems, drones providing reconnaissance ahead of the formation, robotic vehicles performing logistics tasks, or even armed unmanned ground vehicles operating alongside manned platforms. This requires computing capabilities similar to what might be found in data centers rather than military vehicles of previous generations. Fourth, the vehicle's optionally manned capability represents a fundamental shift in how armored vehicles are conceived. Previous vehicles were always operated by humans physically present in the vehicle. The Bradley replacement must support remote operation, where crew members control the vehicle from positions outside it, potentially operating multiple vehicles simultaneously. This doesn't mean the vehicle will normally operate without crews. Human presence provides advantages in judgment, adaptability, and leadership that AI cannot match, but it means the option exists for specific missions or when casualties reduce available crew. Implementing this capability requires sophisticated sensors to provide situational awareness for remote operators, reliable communication systems, and autonomous capabilities that allow vehicles to handle routine tasks without constant human input. The doctrinal implications of these technologies are as significant as the technical capabilities themselves. An infantry fighting vehicle that can operate autonomously, control unmanned systems, and network seamlessly with other platforms changes how commanders employ mechanized infantry. Reconnaissance that previously required risking vehicles and crews might be performed by drones and unmanned vehicles controlled from the OMFV. Suppressive fire that required exposing crews to enemy fire might be delivered remotely. Infantry might dismount farther from objectives, using the vehicle's networked sensors to maintain situational awareness while approaching on foot. These possibilities require new tactics, techniques, and procedures that the Army is developing concurrently with the vehicle itself. The path to the current optionally manned fighting vehicle program winds through multiple false starts, cancelled programs, and lessons learned from decades of attempting to replace the Bradley. Understanding this history provides context for why the current program is structured as it is and what challenges it seeks to avoid. The first serious attempt to replace the Bradley was the Future Combat Systems Program, an ambitious early 2000s initiative that sought to create an entire family of manned and unmanned vehicles connected through an advanced network. FCS envisioned a lightweight, highly networked force where information superiority would substitute for heavy armor. The manned ground vehicle component of FCS would have replaced both the Bradley and the M1 Abrams tank, with variants on a common chassis weighing approximately 20 tons, less than half the weight of vehicles they would replace. This dramatic weight reduction would be enabled by advanced networking that allowed vehicles to detect and engage threats before being targeted themselves, plus active protection systems to defeat any weapons that did reach them. FCS was cancelled in 2009 after billions in investment produced impressive technology demonstrations but no production-ready vehicles. The program's fundamental problems were multiple. The technologies required weren't mature enough to be reliable, the lightweight vehicles couldn't survive realistic threat environments, and the assumption that networking could substitute for armor proved optimistic when networks might be disrupted by enemy electronic warfare. The cancellation was painful but educational. It taught the Army that revolutionary approaches sound appealing, but evolutionary improvements on proven concepts are more likely to produce usable systems. Following FCS cancellation, the Army pursued the Ground Combat Vehicle program, which sought to replace the Bradley with a more conventional design. GCV requirements emphasized survivability and payload capacity, accepting that a vehicle capable of protecting its crew and passengers from realistic threats would be heavy, potentially 40 to 50 tons or more. The program progressed through early design phases, but was cancelled in 2014 due to cost concerns and questions about whether such a heavy vehicle would be deployable or affordable in realistic numbers. The experience reinforced that there are no easy solutions. Lightweight vehicles are vulnerable, heavy vehicles are expensive and hard to deploy, and finding the right balance is extraordinarily difficult. Between these major programs, the Army implemented numerous Bradley upgrade initiatives that added armor, improved the gun system, enhanced situational awareness, and addressed other capability gaps identified through combat experience in Iraq and Afghanistan. These incremental improvements kept the Bradley relevant but didn't address fundamental limitations. By the mid-2010s, the consensus had formed that a new vehicle was necessary, but that the approach needed to be more pragmatic than FCS, while avoiding the excessive weight and cost that doomed GCV. The Next Generation Combat Vehicle Initiative emerged from this history as an umbrella for multiple programs addressing different parts of the Army's armored force. The Optionally Manned Fighting Vehicle program focuses on replacing the Bradley in mechanized infantry units. The Mobile Protected Firepower program addresses light infantry units' need for direct fire support. The Robotic Combat Vehicle program develops unmanned ground vehicles for various missions, and future programs will eventually address tank replacement, though that effort remains in early conceptual stages. This family of vehicles approach learned from FCS that common chassis aren't always practical, but that vehicles should be designed to work together as systems. The decision to make the Bradley replacement optionally manned reflected several factors. First, autonomous technology had matured significantly since FCS, with self-driving cars and military drones demonstrating that autonomous operation was achievable, even if not yet perfected. Second, the Army recognized that while full autonomy might not be reliable enough for all missions, reducing crew sizes or allowing remote operation could provide tactical advantages in specific scenarios. Third, designing for optional manning from the beginning was judged easier than trying to add such capabilities to an existing manned design. Fourth, the flexibility of being able to operate vehicles with or without crews present provided options that might prove valuable in ways not fully anticipated during requirements definition. The competitive prototype phase that began in 2022 represented a deliberate attempt to avoid premature commitment to a single design. By funding two competing teams to develop actual vehicles, rather than just paper designs, the Army hoped to see different approaches to the requirements and make final selection based on demonstrated performance rather than proposals. This approach is more expensive in the short term, Paying two contractors to develop prototypes costs more than selecting one design early, but potentially reduces long-term risk by ensuring the selected design actually works as promised before committing to full-scale production. The two competing teams took distinctly different approaches to meeting the requirements. The American Rheinmetall Vehicles and Point Blank Enterprises team based their design on the Lynx infantry fighting vehicle that Rheinmetall had developed for export markets. This approach offered the advantage of building on proven technology that had already been tested and refined, reducing some technical risk. The vehicle could be scaled up or modified to meet American requirements while leveraging existing design work. The team emphasized modularity and the vehicle's ability to accept different weapon systems, armor packages, and internal configurations based on mission needs. The General Dynamics Land Systems and BAE Systems team developed a clean sheet design incorporating technologies from both companies' extensive experience with armored vehicles. GDLS manufactures the M1 Abrams tank and has been involved in every major American armored vehicle program for decades. Bear Systems brings expertise in active protection systems, advanced weapons, and electronic systems. Their design emphasized integration of these various technologies into a coherent system optimized for the requirements rather than adapting an existing vehicle. The team highlighted their vehicle's growth potential, the ability to incorporate future technologies as they mature, and its compatibility with other systems in the Army's inventory. Both designs incorporated large 30mm or similar caliber main guns rather than the Bradley's 25mm weapon, reflecting the reality that potential adversaries have improved their armored vehicles to the point where 25mm rounds are marginally effective. Both featured advanced fire control systems with thermal imaging, laser rangefinding, and automatic target tracking capabilities far beyond what the Bradley possesses. Both included provisions for active protection systems, though the specific systems and how they integrated with vehicle architecture differed. Both designs emphasized networking capabilities and the computing power necessary to support them. The testing and evaluation process for these prototypes is examining multiple dimensions of performance. Mobility testing assesses whether vehicles can travel cross-country at required speeds, whether they can negotiate obstacles and terrain, and whether they're reliable enough for sustained operations. Survivability testing evaluates how well armor and active protection systems defeat various threats at different angles and ranges. Lethality testing measures the effectiveness of main gun and anti-tank weapons against representative targets. Network testing validates that vehicles can communicate reliably and that their computing systems can process information at required rates. Human factors testing ensures that crews can operate the vehicles effectively and that the ergonomic support rather than hinder performance. One particularly challenging aspect of testing involves validating the autonomous and remote operation capabilities. How well can the vehicle navigate cross-country without human input? How effectively can a remote operator control the vehicle using only sensor feeds? What happens when communications are disrupted? Can the vehicle continue its mission autonomously, or does it halt? How many vehicles can a single operator control simultaneously, and what are the implications for force structure? These questions don't have simple answers and require extensive testing under realistic conditions to answer properly. The program timeline calls for prototype testing through 2024-2025, with a production decision expected in the mid-2020s and initial operational capability potentially by 2030 or shortly thereafter. However, these timelines are optimistic and assume testing reveals no major problems requiring redesign. Given the complexity of the systems involved and the ambitious nature of the requirements, some observers expect delays as technical challenges emerge and are addressed. The Army has expressed commitment to the program, but also recognizes that delivering capability on time is less important than delivering capability that works. Rushing a flawed design into production would repeat mistakes from previous programs. The broader Next Generation Combat Vehicle Initiative, of which OMFV is one component, reflects the Army's recognition that transforming armored warfare requires more than just new vehicles. New doctrine must be developed, explaining how these vehicles will be employed. New organizational structures might be needed to support different crew sizes or the integration of manned and unmanned systems. New training methods must be created to prepare soldiers to operate vehicles with capabilities far beyond anything currently in the inventory. New maintenance procedures and logistics systems must support vehicles with complex electronic systems and modular components. The Army is working on all these elements in parallel with vehicle development, recognizing that hardware alone doesn't create capability. The development of the Army's next-generation Bradley replacement involves several fundamental themes that illuminate broader questions about military innovation, technological change, and the future character of warfare. The first theme concerns the challenge of designing for threats that don't yet exist. The OMFV won't reach full operational capability until 2030 at the earliest, and the vehicles will serve for decades thereafter, potentially until 2060 or beyond. This means the vehicle must be effective against threats that are currently in development or haven't even been conceived yet. Predicting future threats is notoriously difficult, and history is littered with weapons systems optimized for scenarios that never materialized while proving inadequate for conflicts that actually occurred. The solution is designing for adaptability, creating vehicles with enough growth potential to incorporate future technologies and enough modularity to be reconfigured as threats evolve. But adaptability itself is difficult to quantify and test, making it hard to determine whether proposed designs truly possess it. The tension between air deployability and survivability exemplifies the compromises inherent in any military vehicle design. The Army wants vehicles that can be loaded onto C-17 cargo aircraft and flown anywhere in the world on short notice, enabling rapid response to crises. But C-17s have weight and size limitations that constrain vehicle design. Heavier armor improves survivability, but adds weight that makes air transport difficult or impossible. The modular armor approach attempts to square this circle by allowing vehicles to deploy with minimal armor and add protection after arrival. But this creates its own challenges. The additional armor must be transported somehow, it must be stored where it's needed, and it must be installable quickly enough to be practical. Whether this approach works in practice or proves cumbersome remains to be seen. The second theme involves the integration of artificial intelligence and autonomous capabilities into manned vehicles. The optionally manned designation sounds straightforward, but conceals profound questions about human-machine interaction. How much autonomy should the vehicle have? In what situations should it be allowed to make decisions without human input? How do crews transition between manual and autonomous modes? What happens when autonomous systems fail or behave unpredictably? These questions have both technical and ethical dimensions. Technically, the AI must be reliable enough that crews trust it while remaining robust enough to function even when sensors are degraded or networks are disrupted. Ethically, decisions about when to use lethal force should remain with humans, but autonomous systems make decisions so rapidly that human oversight becomes difficult to maintain meaningfully. The trust issue is particularly challenging. Studies of autonomous systems in various contexts show that humans tend to either over-trust automation, delegating decisions they should make themselves, or under-trust it, refusing to use capabilities that would improve performance because they don't believe the systems will work properly. Building appropriate trust requires transparency about what the autonomous systems can and cannot do, training that develops accurate mental models of system capabilities, and interfaces that make automation status clear. The OMFV's designers must address these human factors issues alongside the technical challenges of creating autonomous capabilities. The third theme concerns networking and the assumption that vehicles will always be connected to broader information networks. The OMFV's design assumes it will receive information from multiple sources beyond its own sensors. Other vehicles, drones, satellites, and command posts will all feed data that the vehicle's computer systems will integrate into comprehensive situational awareness. This networked approach offers tremendous advantages when it works, potentially giving crews better understanding of the battlefield than any previous generation of soldiers possessed. But it also creates vulnerabilities. What happens when networks are disrupted by enemy electronic warfare or cyber attacks? Does the vehicle become less effective than legacy systems that weren't designed around networking assumptions? Or do the onboard sensors and autonomous capabilities provide enough capability to operate independently if necessary? This question reflects broader tensions in modern military thought between network-centric warfare concepts that emphasize information sharing and traditional approaches that stress independent operation by decentralized units. The ideal is probably a hybrid, vehicles that gain advantages from networking when available, but remain capable of independent operation when networks fail. But designing for both scenarios is difficult, and testing whether designs truly achieve this balance is challenging because it requires simulating realistic network disruption that goes beyond simple communications failures to include the confusion and degraded situational awareness that would occur in actual combat. The fourth theme involves the economics of advanced military systems and whether the Army can afford to procure the OMFV in numbers adequate for operational needs. Modern armored vehicles are extraordinarily expensive, with unit costs potentially exceeding $10 million per vehicle for advanced designs with all the required capabilities. The Army operates thousands of Bradleys currently and would need to procure similar numbers of replacements to maintain mechanized infantry capabilities. At $10 million per vehicle, a fleet of 3,000 would cost $30 billion just for initial procurement, not including decades of operating costs, maintenance, and upgrades. Whether defense budgets can support investments of this magnitude while funding aircraft, ships, and all the other capabilities the military requires is questionable. This economic reality drives interest in trade-offs and alternatives. Could the Army buy fewer advanced vehicles and supplement them with less capable but cheaper platforms? Could existing Bradleys continue in service longer while new vehicles are procured gradually? Could some missions be performed by unmanned vehicles that are cheaper because they don't require crew protection? These questions don't have clear answers, but they illustrate that technological possibility doesn't guarantee fielding. Programs must be affordable within realistic budget constraints, or they won't survive regardless of capability. The fifth theme concerns the changing character of armored warfare itself and whether traditional concepts of tanks and infantry fighting vehicles remain relevant. Some analysts argue that the proliferation of anti-armor weapons and the transparency of modern battlefields make armored vehicles increasingly vulnerable and obsolete. They point to recent conflicts where armored forces suffered heavy losses to anti-tank guided missiles, drones, and precision artillery. If every vehicle can be detected and targeted, they argue, survivability becomes impossible regardless of armor or active protection. The implication is that future ground forces might emphasize dispersion, light forces that are harder to target, and standoff weapons that engage from beyond the range of enemy systems. The counter-argument is that armored vehicles remain essential for seizing and holding ground, that survivability through mobility and active protection remains achievable, and that abandoning armor would concede decisive advantages to adversaries who continue developing armored capabilities. This debate influences OMFV development because the program's fundamental premise is that advanced infantry fighting vehicles will remain relevant. If that premise is wrong, the entire program represents misallocation of resources. Resolving this debate requires judgment about future warfare's character that goes beyond technical analysis to include strategic assessment of how wars will be fought and what capabilities will prove decisive. The sixth theme involves the human dimensions of introducing radical new capabilities into military organizations. Even if the OMFV meets all technical requirements and proves effective in testing, success ultimately depends on soldiers being able to operate it effectively in combat. This requires training programs that prepare crews for capabilities far beyond what current vehicles possess. Doctrine that explains how to employ these capabilities in various scenarios and organizational cultures that embrace, rather than resist, the changes the vehicle represents. Military organizations are often conservative, preferring proven approaches over untested innovations. Overcoming this conservatism requires demonstrating that new capabilities offer clear advantages while managing the transition in ways that don't disrupt operational readiness. The crew size implications of optionally manned operation illustrate these challenges. If vehicles can operate with reduced crews or be controlled remotely, does that mean mechanized infantry units need fewer personnel? Do soldiers saved from crew positions get reallocated to other duties, or do force structures shrink? What happens to traditional specialties like vehicle commanders or gunners if their roles can be performed autonomously? These questions affect careers, unit cohesion, and military culture in ways that extend far beyond technical performance. Managing these human dimensions of change is as important as solving technical challenges. The seventh theme concerns the relationship between offensive and defensive capabilities in modern warfare. Every advance in offensive weapons, more effective missiles, better sensors, longer ranges, drives demand for improved defenses, which in turn prompts development of even better offensive systems in endless cycles of action and reaction. The OMFV represents one side of this dynamic, incorporating active protection and other defenses against current threats. But adversaries won't be static. They will develop countermeasures to active protection, sensors that can detect vehicles regardless of signature reduction efforts, and weapons that can overwhelm defenses through saturation or other means. The vehicle's ability to evolve and incorporate improved defenses as they're developed is crucial to maintaining effectiveness throughout its service life. The technical and operational solutions being developed for the OMFV address the challenges and themes outlined above through specific design choices, technologies, and operational concepts. Understanding these solutions provides insight into how the Army is attempting to create a vehicle that meets extraordinarily demanding requirements while remaining affordable and practical. The first major solution involves modular architecture that allows major vehicle components to be changed based on mission requirements. This modularity extends across several dimensions. Armor protection can be configured differently, with minimal armor for deployments where survivability threats are low or weight is critical, and heavier armor packages for high-threat environments where protection is paramount. The main gun and weapon systems can potentially be changed, swapping a 30mm chain gun for a larger caliber weapon, or adding anti-tank missiles, or incorporating directed energy weapons as they mature. Internal arrangements can be reconfigured to carry different numbers of passengers, more ammunition, or specialized equipment, depending on whether the vehicle is being used for mechanized infantry, reconnaissance, or other roles. This modularity requires sophisticated design at the fundamental chassis level. The vehicle structure must accommodate different payloads and weight distributions without compromising performance. Electrical and mechanical interfaces must be standardized so that swapping components doesn't require extensive modifications. Software and computing systems must be able to recognize and work with different configurations automatically rather than requiring manual programming for each variant. The engineering required to achieve this flexibility is substantial, but the operational benefits, having one basic vehicle that can perform multiple roles rather than requiring entirely different vehicles, justify the complexity. The second solution involves active protection systems as primary defense against anti-tank weapons. These systems use radar, infrared, or other sensors to detect incoming projectiles, then employ either hard kill or soft kill countermeasures. Hard kill systems physically intercept threats by launching small projectiles or deploying nets that destroy or deflect incoming weapons before they reach the vehicle. Soft kill systems use electronic jamming, smoke, or decoys to disrupt the guidance systems of incoming missiles, causing them to miss. The OMFV is being designed with integrated active protection rather than adding it as an afterthought, meaning the vehicle's architecture, power systems, and computing infrastructure all support the protection system from inception. The advantage of active protection is that it can defeat threats without the weight penalty of equivalent passive armor. A tank that can reliably intercept incoming missiles doesn't need armor thick enough to stop those missiles from penetrating, allowing weight savings that can be used for other capabilities or reduced to improve mobility and deployability. The disadvantages are that active protection systems can be exhausted by saturation attacks, where more threats arrive than the system can engage. They may be vulnerable to countermeasures, and they add complexity and cost. The OMFV's design assumes these trade-offs favor active protection, at least as a complement to passive armor, though the vehicle will still have substantial conventional armor for threats that active protection cannot address. The third solution addresses networking and autonomous operation through advanced computing architecture and software systems. The vehicle incorporates computing power that would have seemed absurd in previous generations of military vehicles, processors capable of analyzing sensor data in real time, memory sufficient to store detailed map databases and threat libraries, and networking hardware that can maintain connectivity even in contested electromagnetic environments. The software architecture uses modular, updatable code that can be improved over the vehicle's lifetime rather than being static, allowing capabilities to evolve as better algorithms and AI systems are developed. The autonomous capabilities being developed include multiple levels of automation. At the lowest level, the vehicle can assist human crews with routine tasks like navigation, maintaining formation with other vehicles, or monitoring sectors for threats. At intermediate levels, it can execute specific tasks like moving to designated positions, engaging identified targets under human authorization, or conducting reconnaissance within specified boundaries. At the highest levels, it could theoretically conduct entire missions with minimal human oversight, though the Army is cautious about allowing this degree of autonomy, except in very specific circumstances. The key is flexibility. Crews can adjust how much autonomy they delegate based on situation and comfort level. The fourth solution involves the human-machine interface and how information is presented to crews. Modern vehicles risk information overload. With multiple sensors, networking data from other platforms, active protection systems providing warnings, and autonomous systems requesting decisions, crews could be overwhelmed by data. The OMFV's designers are developing interfaces that filter and prioritize information, presenting crews with what they need to know, rather than everything the vehicle's systems are detecting. This involves artificial intelligence that can distinguish between routine events and critical threats, interfaces that use visual, audio, and even haptic feedback to convey information efficiently, and controls that allow intuitive operation without extensive training. Augmented reality displays are being incorporated, potentially through helmet-mounted systems that overlay symbology onto the real world, or sensor feeds, highlighting threats, showing navigation routes, and displaying status information without requiring crews to look at separate displays. Voice control allows crews to issue commands and request information without needing to manipulate controls manually, important when hands are occupied with other tasks. The goal is creating interfaces that enhance rather than hinder human performance, recognizing that even the most sophisticated technology is only useful if crews can actually operate it effectively under the stress of combat. The fifth solution addresses the vehicle's signature across multiple domains, making it harder to detect with visual, thermal, radar, and acoustic sensors. Signature reduction in modern armored vehicles is challenging because they're large, hot from engines and systems, and create substantial radar returns. The OMFV employs several techniques. Angular surfaces that reflect radar energy away from transmitters rather than back toward them, materials that absorb rather than reflect electromagnetic energy, thermal management systems that reduce infrared signature, and acoustic damping that reduces engine and track noise. These measures can't make the vehicle invisible, but can reduce detection ranges, buying time and distance that translate into tactical advantages. The vehicle's signature management extends to the electromagnetic spectrum. Radio transmissions, radar emissions, and other electromagnetic activities can reveal presence and potentially provide targeting information to enemies. The OMFV's communication systems use frequency hopping, directional antennas, and low probability of intercept waveforms to minimize electromagnetic signature. The vehicle can operate in electronic silence when necessary, relying on passive sensors and preloaded mission data rather than continuous communications. Balancing the benefits of networking against the vulnerabilities created by electromagnetic emissions requires sophisticated management that the vehicle's systems handle with minimal crew input. The sixth solution involves weapons systems that provide overmatch against current and anticipated threats. The main gun, whether 30mm, 40mm, or even larger calibers being tested, fires programmable ammunition that can be set to airburst above targets, penetrate light armor, or explode on delay after penetrating structures. This ammunition flexibility means one weapon system can effectively engage infantry in open or urban terrain, light armored vehicles, low-flying aircraft and drones, and even with the right ammunition, main battle tanks if necessary. Anti-tank guided missiles provide long-range precision engagement capability against heavy armor. The potential for directed energy weapons, lasers powerful enough to destroy drones and missiles, is being explored for future integration. The fire control system incorporates automatic target detection and tracking, slaving the gun to identified threats and maintaining aim even while the vehicle is moving across rough terrain. The stabilization systems that enable firing while moving have improved dramatically from previous generations, with sophisticated gyroscopes and accelerometers that compensate for vehicle motion in real time. The fire control computer calculates firing solutions, accounting for range, target motion, wind, temperature, and even the wear state of the gun barrel, providing first-shot hit probabilities that previous vehicles couldn't achieve. Combined with modern ammunition, this means the OMFV can engage and defeat threats at longer ranges and with higher confidence than the Bradley ever could. The seventh solution addresses logistics and maintenance through design choices that reduce support burdens. The vehicle uses common components when possible, shares parts with other systems in the Army's inventory, and is designed for modular replacement of failed components rather than complex repairs in the field. Diagnostic systems can identify problems before they cause failures, allowing preventive maintenance rather than reactive repairs. The autonomous capabilities include self-diagnosis. The vehicle can report its own maintenance status, predict when systems are likely to fail, and even in some cases reconfigure itself to work around problems until proper repairs can be performed. The support infrastructure being developed alongside the vehicle includes mobile maintenance facilities that can travel with deployed units, spare parts packages optimized for the most common failures, and training for mechanics that emphasizes troubleshooting and module replacement, rather than detailed component-level repair. The goal is keeping vehicles operational with reasonable maintenance burden, rather than requiring excessive logistics tail that would constrain operational tempo. Whether these goals can be achieved remains to be tested. Modern vehicles' complexity inherently makes them harder to maintain than simpler predecessors, and there may be irreducible trade-offs between capability and supportability. The OMFV program, ambitious and technologically sophisticated as it is, deserves critical examination regarding its assumptions, potential weaknesses, and place within broader Army modernization efforts. The first critique concerns technological optimism and whether the systems required for the OMFV will mature sufficiently for reliable operational use by the time the vehicle is scheduled to enter service. Artificial intelligence, autonomous operation, active protection, advanced networking, and modular architecture are all technologies that work in controlled testing, but might prove brittle under the chaos and stress of actual combat. Military history includes numerous examples of systems that performed well in development, but failed in operational service because real-world conditions exposed weaknesses that testing didn't reveal. The complexity of the OMFV, the integration of multiple advanced technologies that must all work together reliably, magnifies these risks. This technological risk is compounded by the accelerated timeline. The Army wants the vehicle operational by 2030, which provides limited time for the iterative testing, refinement, and fixing of problems that typically characterize complex systems development. Pressure to meet deadlines can lead to accepting vehicles with known deficiencies, planning to fix them later, but experience shows that deferred problems often don't get resolved because attention and funding move to the next priority. The alternative, extending timelines to ensure systems are mature, means continued reliance on aging Bradleys and delayed realization of the capabilities the new vehicle is supposed to provide. There is no easy resolution to this tension between speed and thoroughness. The second critique involves the optionally manned concept and whether it provides genuine operational advantages or is primarily a technological demonstration of capabilities that won't be used. The scenarios where completely autonomous operation or remote control might be preferable to having crews physically present in vehicles are limited. Urban combat or other scenarios where every vehicle is likely to be engaged might benefit from remote operation that doesn't risk crews. But these are situations where autonomous systems would likely struggle with the complexity and unpredictability of the environment. Open terrain combat, where autonomous systems might function better, probably doesn't provide the same urgency for removing crews from vehicles. The flexibility of having the option for unmanned operation has value, but whether it justifies the complexity and cost required to implement it is debatable. The reduced crew operations that might be more practical than full autonomy, having one person operate multiple vehicles, or having smaller crews with automated systems handling roles traditionally performed by crew members, face different challenges. Will commanders actually trust autonomous systems enough to routinely employ these capabilities, or will they insist on full crews for any important mission? Will the training and organizational changes required to support different crew sizes be implemented, or will the Army default to traditional approaches? The optionally manned capability might end up like many advanced features that get incorporated into designs but rarely used because doctrine, training, and culture haven't adapted to enable their employment. The third critique concerns deployability and whether the modular armor approach truly makes the vehicle rapidly deployable by air. The concept is elegant. Deploy with minimal armor to reduce weight, add protection after arrival. But practical implementation faces challenges. The additional armor must be transported to wherever vehicles are being deployed, which requires strategic airlift capacity that might be unavailable during crises. The armor must be stored somewhere until needed, creating logistics and security challenges. The installation process, even if streamlined, takes time and requires facilities and equipment that might not be present in austere locations. The vehicle in minimal armor configuration might be vulnerable during the period between arrival and armor installation. Moreover, the assumption that initial operations can be conducted with minimal armor might prove incorrect if conflicts begin with intense combat rather than gradual escalation. If the opening phases of a conflict involve heavy fighting immediately upon deployment, vehicles arriving in lightweight configuration would be inadequate regardless of how quickly armor could theoretically be added. The modular armor concept works best for scenarios where there's time for methodical build-up before combat intensity increases, but such scenarios might not reflect realistic operational demands. The fourth critique addresses cost and affordability. Early estimates suggest the OMFV might cost $8 to $12 million per vehicle, though final costs won't be known until production contracts are negotiated. At these prices, procuring the 3,000 or more vehicles needed to replace the Bradley fleet would require $30 to $40 billion just for procurement, not including decades of operating and support costs. Whether defense budgets can support expenditures of this magnitude while funding all the other modernization priorities the Army has identified is questionable. The risk is that the program produces a capable vehicle, but in numbers inadequate for operational needs, because full procurement is unaffordable. This affordability challenge might lead to uncomfortable trade-offs, buying fewer vehicles and accepting capability gaps, extending procurement over longer periods, and operating mixed fleets of old and new vehicles, or accepting less capable designs that are more affordable. Each option has disadvantages. Capability gaps mean some units lack modern equipment and might not be as effective. Mixed fleets create logistics and training burdens. Less capable vehicles might not provide the advantages the program is intended to deliver. The Army hasn't clearly articulated how it will manage these trade-offs if costs prove higher than budgets allow. The fifth critique concerns the assumption that mechanized infantry centered on infantry fighting vehicles remains the right organizational approach for future ground combat. Perhaps the proliferation of anti-armor weapons and battlefield transparency means that concentrating infantry in armored vehicles makes formations vulnerable to massed precision fires that can destroy entire units before they close with enemy forces. Perhaps future ground combat will emphasize dispersion, with small units operating independently, supported by unmanned systems, employing standoff weapons rather than closing to direct fire range. If so, the entire premise of the OMFV, creating an advanced infantry fighting vehicle, might be addressing yesterday's operational concepts rather than tomorrow's realities. This critique doesn't have a definitive answer because future warfare's character is inherently uncertain. Military organizations must make judgments about what capabilities they'll need and commit resources to developing them, despite incomplete information about whether those judgments are correct. The OMFV represents a bet that armored vehicles remain relevant, that improvements in protection and networking can overcome increased threats, and that mechanized infantry will continue to be decisive in future conflicts. History will judge whether this bet was correct, but the decision must be made now based on current understanding and imperfect predictions. The sixth critique involves the potential vulnerability of networked systems to cyber attack and electronic warfare. The OMFV's design assumes vehicles will be connected to networks that provide data from multiple sources. But those networks are potential targets for adversaries who might use cyber attacks to corrupt data, electronic warfare to disrupt communications, or other means to degrade the networking that the vehicle's concept depends on. If enemies can blind the vehicle's sensors, corrupt its situational awareness, or prevent communication with other friendly forces, many of the capabilities that distinguish it from legacy vehicles would be negated. The program includes countermeasures, cybersecurity, electronic warfare resilience, ability to operate independently when networks are unavailable. But adversaries constantly develop new attack methods, and the battle between offensive and defensive cyber capabilities is ongoing. The question isn't whether the OMFV will have some protection against these threats, but whether that protection will be adequate when facing sophisticated adversaries employing their latest capabilities. The transparency and connectivity that provide advantages when networks function can become vulnerabilities when they don't, and ensuring the vehicle remains effective across this range of conditions is challenging. The seventh critique concerns the program's relationship to broader Army transformation and whether developing advanced vehicles addresses the most critical capability gaps. The Army faces numerous modernization challenges: artillery systems that lack the range and precision of potential adversaries, air defense capabilities that have atrophied after decades of operating without serious air threats, sustainment systems that struggle to support high-intensity operations, and many others. Resources invested in the OMFV can't be used for these other priorities. Whether the balance is right, whether mechanized infantry capabilities are the most critical need, or whether other capabilities should receive higher priority, is a strategic judgment that goes beyond assessing the OMFV program in isolation. The story of how the Army's next-generation Bradley replacement is taking shape represents far more than the development of a new armored vehicle. It is a case study in how modern militaries attempt to prepare for future warfare, despite profound uncertainty about what that warfare will entail. It illustrates the tensions between technological ambition and practical constraints, between revolutionary concepts and evolutionary improvements, between what's technically possible and what's operationally practical. Most fundamentally, it reflects the reality that preparing for future conflict requires making decisions today based on imperfect understanding of how warfare will evolve, knowing that some of those decisions will prove incorrect, but that failing to decide is itself a choice with consequences. The optionally manned fighting vehicle program is attempting something extraordinarily difficult, creating a vehicle that incorporates technologies still maturing, that addresses threats not yet fully defined, that must balance contradictory requirements for protection and deployability, and that will serve for decades, during which the character of warfare will continue to evolve. The program has learned from previous false starts, the revolutionary ambitions of future combat systems that proved too ambitious, the conventional approach of ground combat vehicle that proved too expensive and heavy, and is seeking a middle path that delivers advanced capabilities while remaining affordable and practical. Whether this approach succeeds remains to be seen. The competing prototypes currently being tested will provide concrete evidence of what's actually achievable rather than just proposed, and the Army's eventual selection of a final design will reflect judgment about which approach best balances the numerous competing factors. But even successful prototypes don't guarantee operational success. Vehicles that work well in testing might prove less effective in service, costs might exceed projections, training and doctrine development might lag behind hardware delivery, and the whole system of systems that the OMFV is supposed to integrate with might not coalesce as envisioned. The human dimension of this transformation deserves emphasis. The crews who will eventually operate these vehicles are currently training on Bradleys, learning tactics and procedures developed for vehicles with far less capability, transitioning them to platforms with autonomous features, advanced networking, and capabilities like active protection that require new operational approaches will challenge individual soldiers and units. The Army's success in developing doctrine, training, and organizational structures that enable effective employment of the OMFV's capabilities will ultimately determine whether the program delivers on its promise. Hardware alone doesn't create military capability. It must be integrated with people, organizations, and concepts to produce effects. The broader transformation of armored warfare that the OMFV represents extends beyond any single vehicle. The integration of manned and unmanned systems, the networking that connects platforms across domains, the autonomous capabilities that enable new operational approaches, and the active protection and advanced weapons that change the calculus of armored combat are all trends likely to continue regardless of the OMFV's specific fate. Even if this particular program encounters difficulties, the capabilities it seeks to deliver will remain priorities, and future programs will pursue them through different approaches. The OMFV is one instantiation of broader ideas about how ground combat will evolve in coming decades. The implications of these changes reach beyond the Army to affect how America thinks about ground power and its role in national defense. If advanced armored vehicles enable mechanized forces to operate effectively despite sophisticated threats, then ground forces remain central to deterrence and warfighting. If, conversely, anti-armor weapons and battlefield transparency make armored vehicles increasingly vulnerable, then ground power must be reimagined around different capabilities, perhaps lighter forces that are harder to target, perhaps standoff weapons that engage from beyond direct fire range, perhaps unmanned systems that accept attrition as inevitable. The OMFV represents a bet on the former vision, but the bet won't be validated until the vehicle faces realistic threats in actual operations. The financial dimension remains perhaps the most challenging aspect of the program. Defense budgets are finite, and resources allocated to the OMFV can't be used for other priorities. The question isn't whether the OMFV would be valuable if cost were no object. Clearly, a vehicle with its proposed capabilities would be useful, but whether the value justifies the expense when so many other needs compete for funding. This calculation involves strategic judgments about threat priorities, operational concepts, and risk tolerance that go well beyond technical assessments of vehicle performance. Different analysts examining the same data can reach different conclusions about whether the program deserves its place in funding priorities. The program's timeline, stretching into the 2030s for initial operational capability and beyond that for full deployment, means that by the time the OMFV becomes the Army's standard infantry fighting vehicle, the Bradleys it replaces will have served for 50 years or more. This longevity reflects both the original Bradley's quality — it has proven adaptable enough to remain relevant through decades of technological change — and the difficulty of developing replacements in an era of constrained budgets and increasingly complex systems. The OMFV faces the challenge of matching this longevity, remaining effective for decades, during which warfare will continue to evolve in ways we cannot fully predict. The technological systems being developed for the OMFV — artificial intelligence, autonomous operation, active protection, advanced networking — are not unique to this program, but represent broader trends affecting all military systems and indeed much of modern society. Self-driving cars, connected devices, machine learning systems, and many other civilian technologies share common foundations with military capabilities. This means the Army is not developing in isolation, but can leverage broader technological progress, while also facing potential adversaries who have access to the same technologies and can develop countermeasures. The arms race between capabilities and countermeasures continues regardless of any single program. The debate about whether the OMFV represents the right approach to modernizing mechanized infantry will continue throughout the program's development and beyond. Skeptics will point to technical difficulties, cost growth, delays, and gaps between promised capabilities and delivered performance as evidence that the program should be restructured or cancelled. Advocates will argue that the capabilities are essential, that problems are normal in complex development programs, and that patience is required to realize transformational capabilities. Both perspectives have merit, and the truth likely lies between them. The program may deliver important capabilities, but not quite as revolutionary or as affordable as originally envisioned. What is clear is that the challenges driving the OMFV program — the need for ground forces that can operate in highly contested environments, the requirement for vehicles that can survive against sophisticated threats, the demand for platforms that can integrate into networked operations — are real and will persist regardless of whether this particular program succeeds. Even if the OMFV encounters insurmountable problems and is cancelled, the Army would need to pursue the capabilities through some other approach. The strategic requirement for advanced infantry fighting vehicles doesn't disappear if one program fails. It just means finding different ways to meet that requirement. The soldiers who will eventually crew these vehicles, who will trust their lives to its protection systems, who will employ its weapons in combat, and who will maintain it under difficult conditions, deserve vehicles that work as promised. This means thorough testing, honest assessment of limitations, and organizational commitment to addressing problems rather than glossing over them. It means training that prepares crews for the capabilities they'll actually have, rather than idealized visions of how systems should work. It means support infrastructure that enables sustained operations rather than platforms that work in peacetime but can't be maintained in war. These requirements seem obvious but are often compromised by schedule pressure, budget constraints, or institutional resistance to acknowledging problems. The story of how the Army's next-generation Bradley replacement is taking shape and changing armored warfare is far from complete. The program remains in competitive development, with major decisions still ahead and years of testing and refinement before operational deployment. Technical challenges will emerge that weren't anticipated, costs will likely grow as they typically do in complex programs. Timelines will probably slip, as is common with ambitious development efforts. Yet despite these almost certain difficulties, the program represents the Army's best effort to prepare for future ground combat, based on current understanding of threats, technologies, and operational requirements. Whether future historians will judge the OMFV as a successful transformation of armored warfare or as another in a long line of ambitious programs that promised more than they delivered depends on decisions not yet made, technologies not yet fully matured, and combat environments not yet encountered. For now, the program proceeds with cautious optimism, confidence that the capabilities being developed are necessary and achievable, tempered by awareness of the challenges and recognition that success is not guaranteed. The transformation of how ground forces fight in the 21st century depends partly on whether programs like the OMFV can deliver on their promise of platforms that combine protection, firepower, networking, and autonomous capabilities in ways previous generations couldn't imagine. The outcome will shape not just American military capabilities, but the broader evolution of warfare in the decades ahead.